A pot that is 100% guaranteed to boil if you leave it alone will never boil, as long as you check on it often enough. In the quantum world, that's a true story. Let's start with an old proverb. A watched pot never boils. It's a joke about how, when you stare at the pot willing it to boil, those few minutes seem to crawl by. In our world, of course, it's an illusion. Watched or not, the water boils exactly the same. But go down to the quantum world where atoms and electrons live and the story changes. If you watch a changing particle often enough, persistently enough, it really does freeze in place. A particle that would have changed if left alone stops in its tracks, for no other reason than that we are looking at it. The phenomenon is called the quantum Zeno effect, named after the paradoxes of Zeno, a Greek philosopher from 2,500 years ago. Zeno argued about a flying arrow. Freeze any single instant, and in that instant the arrow is standing still. If it's standing still at every instant, is the arrow really moving at all? In ancient times, that sounded like a word game. In the quantum world, that word game becomes reality. As long as you keep looking, the quantum arrow cannot fly. Achilles and the tortoise, which we covered recently, was a story about infinitely many steps. Today's is a story about constant observation. Here's today's journey. Almost no equations, will go all the way with just pictures and numbers. Before we dive in, let me pin down just one thing. In the quantum world, to see or to measure means something quite different from everyday usage. In the everyday world, seeing something just means light bouncing off an object and entering your eye. But something as small as an atom is so delicate that the very act of looking disturbs it. Before it's measured, a quantum particle can exist in an in-between state, with several possibilities overlapping at once. That's the famous Schrödinger's cat. Until you open the box, the cat is a superposition of alive and dead. The moment you open the box, it snaps to one or the other. Measurement is the event that collapses overlapping possibilities into one. It's usually called wave function collapse. The name sounds grand, but that one line is all we need today. Now the key scene. Say a particle starts in state A and is slowly changing into state B. If you ask it, are you A or B right now, the particle must give up the mixture and settle on one of the two. And if the change has only just begun, 9 times out of 10 the answer is still A. At that moment the particle snaps back to pure state A, and the clock of change resets to 0. So the stage is set. Now what happens if we measure very, very often? Let me offer an analogy. Let our quantum particle be the water in a pot. The burner is the natural change. Leave the burner on and the water heats up and eventually boils. Crosses completely from A to B. The plot on the left. The boiledness climbs from 0 to 1, and once the set time has passed, it's 100% boiled. For the curious, this curve is called a sine-squared curve. You don't need to know that to follow along. Now take the same pot, but while it heats, we'll lift the lid now and then to check. Has it boiled yet? Every peak is a measurement. The answer comes back not boiling yet, and the boiledness resets to 0. The plot on the right, the pot we peaked at 8 times. Like sawteeth, it rises a little then drops, rises then drops. The peaks never even reach 4%. It keeps getting sent back to square one, so nothing ever accumulates. The exact peak height is the sine of pi over 16 squared, about 0.038. Less than 4% per interval. Of course, even that small chance adds up a little over 8 tries. The overall chance of boiling comes to about 27%. That's far below the 100% you'd get by leaving it alone. And the more peaks you add, the smaller it gets. With 2 peaks it's 75%, with 8 it's 27%, and with 100 peaks it drops all the way to 2.4%. Peak infinitely often and it's 0. The water never boils at all. Which raises a question. We only glanced at it, why does that block the change? The real secret lies in the answer. The key is that quantum change is remarkably sluggish right out of the gate. Picture a car at a standstill. Even with your foot on the gas, for the first instant it barely moves. The distance covered in the first 0.1 seconds is nothing like the distance in the next 0.1 seconds. At the very start, it hardly moves at all. Quantum change works the same way. Right after the start it's close to 0, then it speeds up more and more. To be precise, the probability of changing is proportional not to the elapsed time, but to the square of the time. Why does the square matter so much? Because squaring makes small numbers dramatically smaller. Halve the time and the chance of changing shrinks not to a half but to a quarter. Try it. Start at time 0.1 and keep halving it, and the chance of changing shrinks to about a quarter each time. This one fact explains everything. Let's work out what happens if we peak twice as often. The measurement interval is halved, so the chance of changing in one interval drops to a quarter. But the number of intervals doubles. So the total change is a quarter times 2, that is 1/2. Peak twice as often and the boiling drops by half. The plot on the left shows that sluggish start. Real quantum change hugs the floor near the starting line. If change ran at a constant rate, it would shoot straight up from the start like the gray dashed line. That flatness along the floor is the whole point. The bars on the right, doubling the number of peaks each time, the chance of boiling falls. 175, 47, 27, 14%. Take the ratio to the previous value. 0.75, 0.63, 0.57, 0.54. Closes in on exactly 1/2. Watch without limit, and the probability of staying in A to the very end approaches exactly 1, just as the formula on screen says. If change had run at a constant rate from the start, then no matter how finely you sliced it, the total would have stayed the same. Peaking would have been useless. The sluggish start, that law of squares, is the key that lets observation stop time. Before you file this away as a cute thought experiment, let me be clear. The quantum Zeno effect isn't a blackboard story. It's a phenomenon actually measured in the lab. The name came in 1977, from physicists Mishra and Sudarshan. Even earlier, Alan Turing, the father of the computer, is said to have reached the same conclusion back in the 1950s. But names and calculations aren't enough. The real proof came from the lab. In 1990, Wineland's group at NIST, the U.S. National Institute of Standards and Technology, demonstrated the effect beautifully. They trapped 5,000 beryllium ions and applied radio waves to slowly drive them toward state B. It was tuned so that, left alone, nearly all of them would cross over in about 0.26 seconds. That's the heating time in our analogy. During exactly that window, the team peeked in on the ions along the way using short laser pulses. They raised the count 1, 2, 4 all the way up to 64, and the fraction crossing to be dropped right on prediction. Here are the results. Peak once and it nearly all boils. Peak 64 times and it barely boils at all. The fraction that crossed to be followed this formula. Take 1, subtract cosine of pi over n raised to the power n, and have the result. 2 peaks, 50%. 8 peaks, 23.5%. 64 peaks, 3.7%. It starts at 1 and falls toward 0. Sharp-eyed viewers may have noticed. In the pot chart earlier, 2 peaks gave 75%, but here it's 50%. Both measure the same thing, the fraction that made it to be. The difference is in how the measurement works. Earlier we assumed an idealized measurement that cleanly asks whether it's still a, while the experiment reads the state back with a laser. But the conclusion is exactly the same. The more often you look, the more the change is suppressed. Back to our pot model. Let's line up the sawteeth and see how they change as we raise the number of peaks. With 2 peaks it still boils 75% of the way, with 32 just 7%. The original blog post has a slider you can play with yourself. The stranger the phenomenon, the more myths cling to it. Let's set 3 things straight. First, the observation here is not human consciousness and not a gaze. The phrase "watch it and it stops" makes it sound like a superpower, but it's nothing of the sort. Looking means firing a laser pulse or bringing in a detector, a physical interaction. What fixes the particle isn't a human mind. It's the event of the measuring device physically disturbing the particle. The effect happens just the same even if the experimenter leaves the room. It's a far cry from watching changes reality mysticism. And you don't need to accept any particular interpretation. Plain quantum mechanics gives exactly the same result. Second, surprisingly, there's an opposite effect too. measure with clumsy timing, and far from blocking the change, you can actually make it happen faster. If the interval lines up with the particle's natural rhythm in just the wrong way, observation ends up egging the change on. In 2001, Raisin's group actually observed both the Zeno and anti-Zeno effects in the quantum tunneling of cold atoms. The idea that watching always stops it is only half true. Watch often enough and it stops. Watch at an awkward rhythm and it speeds up. Third, this isn't just a curiosity, it's useful. The biggest headache for quantum computers is that their carefully built quantum states get scrambled by noise from the surroundings. But keep watching the state with well-chosen measurements, and the Zeno effect lets you pin it in place. It's still at the laboratory stage, but the root idea is the same. Watch relentlessly and hold the state inside a safe zone. Zeno's 2,500-year-old wordplay is becoming a cornerstone of future technology. We've come a long way, but the quantum Zeno effect boils down to a single sentence. Quantum change is sluggish at the starting line, and measurement resets that clock of change to zero. So force it to repeat that sluggish start over and over, and the change never gains momentum, it stands frozen in place. How does an arrow that is motionless at every instant ever fly? In the ancient world, Zeno's question was an unsolvable riddle. But the quantum world hands back a strange truth. As long as you keep asking where it is right now, the quantum arrow truly cannot fly. And only at the moment we stop asking does the arrow begin to fly again. A watched pot never boils. A joke made at our expense turns out, in the world of atoms, to be a rule nature actually follows. If you enjoyed today's video, please subscribe, hit like, and turn on notifications. See you in the next story.